Okay, let's get started. So today we are going to have a shorter lecture because what actually is this? Why are there three hours lectures a day and why are two of them on consecutive days? Like this week, I have to teach 11 hours in total because I also did 2 tutorials for the summer school. And then I'm also helping with 4.5 hours of lectures. And then I also have to do research. So just know, 3-hour lectures is a bit, however, on the positive notes, today, about halfway through the lecture, or probably not halfway through the lecture, as the case may be, because it is not going to be a 3-hour lecture, we will finish all of the material that is regularly a part of this course at what would be the halfway point, because it's 15 lectures. So last summer, I taught Calculus B, and there were 2 3-hour lectures a week. And this course has 3 3-hour lectures a week. And I think that this might actually be a mistake because we are getting more lectures in this semester then the course would be taught by hours had it been taught in the fall, for example. So I think there might have actually been a mistake. If this were a 10-lecture course, then look, in lecture 8, we're wrapping up the material and then we do 2 lectures of applications and it's perfect length, right? No, 15 lectures. So let's see what interesting stuff we're going to do for the remaining lectures because I will have to make some stuff up. Okay, so last time we were discussing operators, but that was because I did not talk about inhomogeneous systems. So now we are going to talk about inhomogeneous systems. But before that, 1 second. Okay, amphetamines consumed. Let's go. Inhomogeneous systems. So we are caring about solving the equation x prime is equal to ax plus f, where f is some vector of functions. And in this case, where we aren't even going to assume that a has constant coefficients. So for example, when we were discussing second order differential equations, we talked about the method of variation of parameters in order to solve the inhomogeneous problem. And what we needed to solve the inhomogeneous problem was that we needed all of the solutions to the homogeneous problem. And then we used the variation of parameters method. But we didn't, if we could solve the inhomogeneous system for non-constant coefficients, then the method of variation of parameters worked just as well. Where constant coefficients are going to come in is that in the constant coefficient case, we're actually going to be able to solve the homogeneous system necessary to do variation of parameters. Right. So we start off by solving the homogeneous system. Suppose the homogeneous system which is x prime is equal to ax, has solutions x1 through to xn. And this is the case of an n by n system. Then we're going to use an ansatz. And that's going to be that x is, does anyone want to guess?
Just a bunch of constants, a matrix times the homogeneous solution.
So There's a question of basically how many undetermined coefficients are we going to introduce? And one answer would be to introduce a matrix worth, so n squared worth. It turns out that you actually want to introduce just n undetermined coefficients. And morally, if we think about this, then, well, it's an n by n system, and an n by n system is like a mth order differential equation. Sometimes it can be converted to one, but sometimes it can't be. So it's slightly more general. But we'd expect as many undetermined coefficients as there are dimensions. Now you may say, well, in this case, the coefficients might be matrix valued, but actually the correct answer is to take just u1 times x1. For u, let's say I, t, undetermined coefficients. Coefficient functions. And this is, of course, the trick of variation by parameter, variation of parameters. So what we're going to do is we're going to actually rewrite this. Suppose that x, let's say xi, or maybe xk is a better thing to write. That this as a vector valued function is equal to xk and then the first component of it down through xk to the nth component of it. Except for the fact that we don't have vector arrows anymore. It's just okay. So what happens then is what we're saying, we are saying that x, let's say 1 through to xn is equal to u1 times x1 1 summed through to un xn first components still. And then it's going to be a column vector all the way up until u1 x1 nth components and un xn nth components. However, we can rewrite this in terms of a matrix. This is equal to the matrix x1 1 through to x1 n through to xn 1 through to xnn. Evaluated on the coefficients u1 through to un. And we're going to call this matrix the fundamental matrix associated with the problem. And we're going to denote it with a capital X. And then the U coefficient thing we're going to denote as a vector. So what is the fundamental matrix? If you have n linearly independent solutions to the homogeneous problem, then it is the matrix whose columns are exactly those solutions, right? So X is equal to the basically a matrix whose columns are x1 through to xn. Solutions are the columns. Okay, well, let's see what happens when we have this notion of the fundamental matrix. What we're going to note then is that our each one of these columns satisfies is a solution to the homogeneous problem. So since x, let's say k prime is equal to a x k, it follows that if instead of multiplying by a column vector, we multiply by the fundamental matrix, then what does the left-hand side become? So AX is equal to what?
Is there like it's a product rule, but for like matrices?
So how you think about matrix multiplication is that, let's say you have a matrix and then you have a column here. So the output matrix is going to equal a column. And the way that the entries here are computed is that this entry is going to be this times this, right? And so what happens if instead of one column, you have two columns? Then the entries in here are going to be this times this, whereas the entries in here are going to be this times this. So basically, if you add columns, then these columns just get added here. So what do you get on the left-hand side? So if you put all the x's together, you get x. If you put all of the x primes together, what do you get?
Oh, just x prime. But
Yes. So how matrix multiplication works is that as this is an equality of n by n matrices. And this is actually going to be very useful. This construction of the fundamental matrix is great. So let's look at our ansatz again. Our ansatz is that x is equal to capital X evaluated on the coefficient matrix U. And then x prime becomes, well, so we're going to have to do chain rule because U is in general a function of T as well. And we do get sort of, product rule. We get product rule for matrix multiplication as well. So what it's going to be is it's going to be x prime of U plus x of U prime. Whereas A of x plus f, which is we want to solve the equation that this equals this, right? Well, that becomes A of x of U plus f. And what can we do with this? So what does this equal?
just x prime.
Yeah. So we get x prime of U, which is what we have here, plus f. So the equation is solved when we have that's x prime of U plus x of U prime is equal to x prime of u plus f. But there's the same term on both sides. So that's equivalent to saying just that x of u prime is equal to f. But fact, if the x1 through to xn are linearly independent functions, then they will be pointwise linearly independent. And we'll come to a proof of this later. So for now, we're just going to assume this. So what pointwise linear independence means is that at every single t, this matrix has an inverse. Thus, we can give u prime as x inverse f. Now, once we found this, we have that u prime is equal to a certain function. U prime 1 is equal to a certain function. U2 prime is equal to a certain function. And then this just becomes, reduces to n integrals. And then once we've solved each one of those integrals, we know what the coefficients are, and we can go back to our ansatz and notice that the integrals are going to introduce constants, and the constants are exactly going to be c times each of the solutions to the homogeneous system. So that works out as well. And so this is basically the same story that we saw with just higher order linear equations, not systems. Okay, so let's do an example. And this will be a 2x2 example. So let's consider x prime is equal to x plus 2y, and then y prime is equal to 4x minus y plus 36 e to the 9t over e to the 12t plus 1. So what we have then is that this basically translates into a is equal to 1, 2, 4, -1, and f is equal to 0, and then 36 e to the 9t divided by e to the 12t plus 1. Okay, so let's solve the homogeneous problem. So what we do is we look at determinant a minus lambda I. And what that's equal to is 1 minus lambda times -1 minus lambda, and then -8. And what that's equal to is lambda squared. Then the cross terms cancel out. Then we're going to get -1 minus 8 equals lambda squared minus 9 is equal to which root? I'll write lambda minus 3 first. Okay, And it's a 2x2 system, so we know that's there are going to be single eigenvalues for each one of these. I mean, because there are two separate eigenvalues. So each one has at least a one-dimensional generalized eigenspace, and so they're both just one-dimensional full eigenspaces. Then what? So for lambda equals 3, what we're going to consider is basically we're going to subtract 3 from the diagonal. So we're going to get -2 here, we're going to get 2 here, we're going to get 4 here, and we're going to get -4 here. And the rows are linearly dependent. So what this really gives us is just the constraint that -2a plus 2b is equal to 0. So if we let a equal 1, then b is equal to 1. So 1, 1 is an eigenvector. Cool. So that's lambda equals 3. And now for lambda is equal to -3, what we're going to do is we're going to add 3 to the diagonal. So we're going to get 4, 2, 4, and then literally 2. They're literally the same row. And that's 4a plus 2b is equal to 0. So if we let a equal 1, then b is equal to what?
-2.
Yeah. Cool. So then what we have is I can summarize it as 1, 1 gets sent by a -3i to 0. And 1 -2 gets sent to 0 by a plus 3i. These diagrams help synthesize all of the information, and I like them. So x, we can just write it down directly. For this solution, we're going to get e to the 3t, e to the 3t. And here we're going to get e to the -3t. And here we're going to get -2e to the -3t. So we took particular solutions. We didn't care about general constants. We took two linearly independent solutions and we formed a matrix whose columns are those linearly independent solutions. And I just read them off from these vectors. So what happens is we want x of u prime to equal the thing. So let's invert x. In order to compute x inverse, well, it's a 2x2 matrix, right? So we take 1 divided by the determinants. Now, what is this? This is going to be 3e to the -3, so it's going to be -2. And then these are also going to cancel, so it's going to be -1. And then we're just going to swap these. Put negative signs on the cross-diagonal terms. And so u prime is equal to -1/3 this. Times this. And what that gives us is a -1/3. Now you sort of imagine this coming in here, right? And so what we're just going to get is this multiple of this column. So here we're going to get, well, let's actually keep the 1/3 already inside of here. So overall, these two negative signs cancel out and the 36 becomes a 12. And then there's 9t minus 3t. So it's going to be 12e to the 6t over e to the 12t plus 1. And here, what we're going to have is minus 12t. Minus 12. Then 9 plus 3 is 12. Does that make sense to everyone? So remember, we're calculating this entry as this times this. Well, there's a 0 here, so it's just the second thing. And the other entry is calculated as this times this, so it's just this times that. And then bringing in the -1/3 gives us that. So as a consequence, what U1 is equal to, it's the integral of 12e to the 6t divided by 12e to the 12t plus 1 dt. And what substitution do I make here?
E to the 12t plus 1.
So what's going to happen is that the derivative of e to the 12t plus 1 is
Just
to the,
yeah, so it's e to the 6t.
yeah, that's better. Then du is equal to 6e to the 6t dt. And that completely cancels out the numerator. So we get 6 and 12, so we get 2 times the integral of du over what is 12t in terms of u?
The thing u squared.
U squared plus 1, and that integral is equal to
That's like arcsine.
arctan.
Ooh.
So arcsine is 1 over square root x squared plus 1. Arctan doesn't have the square roots. That's the difference. You can sort of anyway, yeah. And then let's introduce the constants. And so substituting back, that gives us 2 arctan e to the 6t plus c, right? Now u2 is equal to negative integral 12 e to the 12t over e to the 12t plus 1 dt. And I'm going to make the substitution what?
e to the 12t plus 1.
Good. Well, look, if I take the, okay, that works. That works equally well. I was going to do it without the plus 1, but it actually works equally well. So we get 12 e to the 12 t dt. And what that gives us is negative integral du over u, which is negative log u. We're not putting absolute value bars in this course, plus d, which is equal to negative log 12 e to the 12t plus 1 plus d. Okay, so as a result, we found what u1 and u2 are. So x is equal to 2 arctan e to the 6t times what was our first solution? Our first solution was 1 e to the 3t. Then minus, so I'm going to do the constants last. Then e to the minus 3t, and then we get the vector 1 minus 2. And then we get plus c e to the 3t 1 1 plus d e to the minus 3t 1 minus 2, right? And so as a consequence, we can write this as x is equal to 2 well, we had a minus sign at the beginning, right? So after we make the substitution, it's du over u, and then it's log u. I think that this is right. I'm pretty sure this is right. Oh, did I write a t here? E to the 12t plus 1. 12. Oh, I see. There's a 12 that appeared. Yeah, sorry. Yeah, that's good. Thank you. I blindly copied that over. Thanks. Um, yeah. And then y is equal to, well, I guess I can copy this over and modify it accordingly. So what happens is now there's a -2 coefficient here. So it's going to be +2 for that coefficient, and then d is going to become -2d. Yep, that's right. And so that's the solution to the inhomogeneous system. So that's our first example of solving an inhomogeneous system. And the key is that you need to invert a matrix. Basically, once you've solved the homogeneous system, you invert the matrix, then you apply to that, and then you just get a bunch of integrals that you're supposed to do. So that's not bad. It's 638. I'm going to start the next example. So the next example is going to be more interesting. We're going to do a 3x3 system. And I'm going to start by writing it not in matrix form. So let's write x prime is equal to 2x minus y minus z plus e to the t. Y prime is equal to x minus z, and z prime is equal to x minus y. And then plus e to the minus t. So A is the matrix 2, -1, -1, 1, 0, -1, 1, -1, 0. And F is the vector e to the t, 0, e to the minus t. Okay, so determinants of A minus lambda I, and we're going to use the cofactor expansion for this. Because it's actually a bit nicer to write out. We could do the usual diagonal thing, but it's equivalent to the cofactor thing. And I'm doing the cofactor thing along, let's say, the first column. You know what? Let's do it across the first. Let's do it across the first row. That's what I have in my notes. And so this is going to be a bit of exercise in this teleportation technique. So we do 2 minus lambda, then we do the 2x2 matrix space there. Then we have minus, then we have this matrix, -1 minus lambda, 1, 1, because it teleports, and then minus, and then this, and it's this, 1 minus lambda, 1 minus 1. And so that's equal to 2 minus lambda by lambda squared, and then this is going to be -1. This is going to be minus, this is going to be -1 plus lambda. And this is basically the same thing. So here we get rather -1, yep, and then plus lambda. So expanding that out, we get 2 lambda squared minus 2 minus lambda cubed plus lambda plus, and then let's just combine these together. So we get a +2 minus 2 lambda from both of these terms. And that becomes minus lambda cubed. Then let's look at the lambda terms. We have lambda squared, +2 lambda squared. Then lambda minus 2 lambda, we get minus lambda. And then the +2 and the -2 cancel out. So this is equal to, we can factor out a minus lambda. And then we get lambda squared minus 2 lambda plus 1, which factors as lambda minus 1 squared. Good. So for the eigenvalue lambda is equal to 0, we're going to consider this matrix. And we've subtracted 0 from the diagonal, and so we want to find its kernel. Well, I'm going to transform this as, let's keep this to -1, -1. Then if I want to make this 0, so I'm subtracting 1 here. So I'm adding 1/2 here. And I'm also adding 1/2 here. And here I'm subtracting 1 again. So I'm adding 1/2 here. And I'm adding 1/2 here again. Okay, these are linearly dependent. So as a consequence, I get. So notice that in a 2x2 system, if it were degenerate, we just have that one row as a multiple of the other and we'd be done. Here we actually need 2 equations if we're going to solve for one-dimensional eigenspace, because we have 3 unknowns. So 3 unknowns and 2 equations is what gives us a one-dimensional eigenspace, which is what we expect because this is multiplicity 1. So in general, we're actually going to have to cut it down to 2 equations, which is fine. Let's multiply this by 2 just so we get nicer coefficients. And then this we can eliminate because it's a multiple of that. So what that tells us is that 2a minus b minus c is equal to 0. B minus c is equal to 0, and 0 is equal to 0. So b equals c. And then the question is, what is a? Well, let's a be 1. Sure. Then this says 2a is a b plus c, and b and c are equal. So this then b is 1 and c is 1. So 1, 1, 1 is an eigenvalue, is an eigenvector. Let's do lambda equals, what's the eigenvalue? 1. So now I'm going to subtract 1 from the diagonal. So this 2 is going to become a 1, and both of these 1s are going to become -1s. And okay, there's a clear linear dependence between these two. So what we're going to do is let's subtract from this row. So if I'm subtracting 1 here, then I'm adding 1. Oh, shoot. They're literally 3 times the same row. Okay, so we throw away the next 2 equations, and all this says is that a minus b minus c is equal to 0. So there's 1 equation and there are 3 unknowns. So there's going to be a 2-dimensional space of solutions to this system. And basically the question is, so if we let b equal, we can let b and c be whatever we want, and then we get what a is. So let b equal 1 and c equals 0. Then what does a equal?
One.
Yeah, so we get 1, 1, 0. And because there are three unknowns in one equation, we're expecting to find another solution. So let's be equal. What's the natural next choice to let things be equal? B is what, C is what?
Um, 0 and 1.
Yeah, then A is 1 again. And we get 1, 0, 1. So we have three eigenvectors. And as a consequence, we can write down what X is. So X is going to equal, well, this is associated with the eigenvalue 0. So it's just going to be 1, 1, 1. This is associated with the eigenvalue 1. So we're going to get e to the t, 0. And then here we're going to get e to the t 0, e to the t. So this is our fundamental matrix. And we are going to want to invert this fundamental matrix. So how do we invert a 3x3 matrix? Do you remember? What do I write down here?
You add a 3x3 matrix of zeros.
So what do I write here on the right-hand side of this bar?
Like 9 zeros.
No. The identity matrix. Because we're not finding the kernel, we're doing an inverse. That's the catch. If we were finding a kernel, then that's what we do, but we don't want to find the kernel. We want to find an inverse. So we're basically solving for what's the first column of the matrix. In other words, what gets mapped to the identity. Oh, sorry, the first elementary vector, the second elementary vector, and the third elementary vector. So how I'm going to approach this is I'm going to, well, make these entries 0. Then if I do this, I'm going to subtract from here. So I'm going to get 0, 0 minus e to the t. And then here I'm going to get 0 minus e to the t 0. And here I'm going to get 1, 0, 0 because I haven't done anything here. But here I've subtracted one copy of this. So minus 1, minus 1. And it's absolutely imperative that you actually keep track of this because the inverse is going to appear here at the end. Now I'm going to rearrange these rows and I'm going to multiply them by e to the negative t. So this is going to go up here and it's going to become a 1 and there's going to be a 1 here. I haven't done anything to the first row. I've swapped these two, and what I've done is I multiplied by negative e to the negative t. So this becomes e to the negative t. This becomes negative e to the negative t. This becomes e to the negative t. This becomes negative e to the negative t. Okay, and now I subtract the appropriate multiples from here, and I get the identity matrix on the left. And what that's going to cost me is I'm going to have to multiply this by e to the t, right? So I'm going to subtract 1 from here, and then I'm going to subtract 1 from here again. And so overall, that's going to give me -1. Then here, I'm going to add 1, and here I'm going to add 1. Did everyone follow that? Let's see if I did this conversion correctly. Negative 1, 1, 1. Oh, I have 1 second. When I swapped these entries should have swapped as well, because I moved these around. So it should be e to the negative e to the negative t, negative e to the negative t, and those are 0 entries. And it doesn't change what these are, but it does change this. That's what I have in my notes. Okay, so it's time for a break, and then we're going to finish this example after that. But what we currently have is that x inverse is thus negative 1, 1, 1, e to the minus t 0 minus e to the minus t, e to the minus t minus e to the minus t 0. And we will resume at 7:10. Okay, let's get back to it. So we found x inverse, and so what u is equal to is x inverse of f. And so that's this. And then if we look at what our f was in the original problem, it was e to the t0, e to the minus t. And well, let's just calculate that. So here we're going to get minus e to the t plus e to the minus t. So basically it's this times e to the t and this times e to the minus t. Then that's going to give me 1. And that's going to give me minus e to the minus 2t. Then that's going to give me 1. And there's nothing here. So it's just 1. Sorry, this is u prime, not u. So that tells us that u1 is the integral of minus e to the t plus e to the minus t dt, which is minus e to the t minus e to the minus t plus c. u2 is the integral of 1 minus e to the minus 2t dt, which is at t. Then this is going to be, there's a minus 2, so it's going to become a plus 1/2. And just checking. Yep. Plus d. And then u3 is the integral of just 1 dt, which is t plus e. Good. So we have u1, u2, and u3. Now, if you are going to ask, well, okay, what is u? Well, last time we just went directly straight back to our original ansatz. And our original ansatz was basically that it's this u1 times x1 plus u2 times x2, whatever. But there was another way that we could write that ansatz, which is that x is equal to xu, right? That's another way to write that ansatz. It's the same thing as writing it's u1 times x1 plus u2 times x2. So let's actually use that version of it. So x is equal to xu, which tells us that x1, or rather xyz. Then let's go back and pull out what our fundamental matrix was. And then let's pull out what our entries are. So they're negative e to the t minus e to the minus t plus c, t plus 1/2 e to the minus 2t plus d, and then t plus e. And here's actually a cool trick for writing the answer. We are going to write that it's equal to something plus x times CDE, because that's sort of long to write out. But let's just calculate what some stuff is. So if we do this matrix multiplication, ignoring the constants and just looking at this stuff, minus e to the t minus e to the minus t plus e to the t times t plus 1/2 e to the minus 2t, and then plus e to the t times t. What that's equal to is going to be, well, let's look at e to the t. So e to the t is there's going to be two t's from here and from here. And then there's also going to be this -1. Then for e to the minus t, we have a -1 and then a plus 1/2, because this t times this is e to the minus t. So overall, we get a minus 1/2 e to the minus t. And that accounts for all of the entries. Then for the next one, we're going to get minus e to the t minus e to the minus t. Then we're going to have e to the t times this. And the difference is that we're going to be missing this term. So that 2 is going to be a 1. Minus t. And then in the last entry, we're going to have minus e to the t minus e to the minus t. And then we're going to have t e to the t. Which is going to be e to the t by t minus 1 again, minus e to the minus t. So we can say that x, y, z is equal to these three things. E to the t, 2t minus 1 minus 1/2 e to the minus t, e to the t, t minus 1 minus 1/2 e to the minus t, e to the t, t minus 1 minus e to the minus t. But we're not done yet. We're also going to put the fundamental matrix and I would accept this solution times the constants. It's sort of almost too boring to write out entirely. This is an acceptable solution in this form. This is fine. So that solves this example. So that's a 3x3 system. Now, in principle, there's nothing special about 3x3. This is a perfectly general method. So now you know how to solve arbitrary dimensioned inhomogeneous linear systems of constant coefficients. Now, here we're going to do something really cool. And we're going to talk about matrix exponentials. And so the idea is that if we have an equation like y prime is equal to cy, then what's the solution? Or let's say alpha y. Then what is y equal to?
E to the alpha t.
Yeah. And then we can put some constant here, which is sort of optional. If we want the general solution, it would be this. But this. Let's forget about this for now. Okay, and so when we were solving for constants, coefficients, linear systems, the equation is that x prime is equal to ax. Therefore, let's not write it like this. Let's write it in the way that we were writing it before. The fundamental matrix is equal to its derivative is equal to ax, right? So now we're in matrix land. Therefore, it follows that the fundamental matrix is equal to what?
X prime times A inverse. I mean, A inverse times X prime.
No, I'm looking at the previous line. Just do the most direct thing that you could do from the previous line.
Okay. E to the A
times t as a function of t. Okay, so like what? Does this make sense? So if this makes sense, then I've just given you a methods to solve differential equations by calculating this expression. So this should give the fundamental matrix, which gives you a linearly independent set of solutions. Okay, does this work? What is e to the x anyway? E to the x can be defined as a power series. So it's the sum from n is equal to 0 to infinity of x to the n divided by n factorial, right? And this is always convergent, converges everywhere. So it follows that if we consider e to the at, then this should be defined by a power series as a to the n t to the n divided by n factorial. And as it turns out, this will also converge everywhere. So this is known as the matrix exponential. It's just defined by this series, and it's defined everywhere. So by the way, let's see if this solves the problem. So if we take e to the at and we take its derivative, then we're going to differentiate this power series term by term with respect to t, right? So what that's going to give us is the sum. Now, what we're going to do is A is just constants. We are using that it's a constant coefficient system here, in a very crucial way. So we're not going to get a product rule thing because it's just a constant matrix. So it's going to be a to the n, t to the n minus 1. divided by, well, we're going to get an n up here, and then that's going to cancel with the n factorial to give us n minus 1 factorial. Now, the catch is, if we look at the term that had n equals 0, then that was just a constant, right? And the derivative of a constant is 0. So we can make this sum index from n is equal to 1 to infinity, because the n equals 0 term is 0. Well, here it wouldn't make sense, strictly speaking, because the derivative of a constant is not t inverse. So this formula is true only when we make it is sum from n equals 1. But now what we can do is we can just take out a multiple of a from outside of this. And then we're going to get the sum from n is equal to 1 to infinity of a to the n minus 1, t to the n minus 1 divided by n minus 1 factorial. And what we can do now is we can just shift all of the indices, make it a sum from n equals 0. So we're making the substitution, n plus 1, it gets replaced with n. So if this is a sum from k, you know what, here, I'll do it rigorously. If this is a sum from k equals 0, then k is equal to, so if n is 1, then k is 0. So k is equal to n minus 1 is the substitution that's being made. I'll write this in blue.
I guess it's very similar to how they for e to the I.
Yeah, you can also justify Euler's formula by knowing what the power series for cosine and sine is. And then you can actually see that, for example, e to the it, if you just plug it in to the power series, it's equal to the power series of cosine plus the power series I times the power series of sine. So that exactly happens as well. So power series are a good way of reasoning with sines, cosines, and exponentials in general. Was that what you were saying? Okay, well, that's equal to a e to the, and then this is a t, right? So it satisfies the equation. Thus, e to the at satisfies x prime is equal to ax, right? That's the equation that we had at the beginning. So bam, look, if you can calculate this expression, then that is one perfectly valid way of solving the system. Now, does it give linearly independent solutions? That's the question, because maybe it gives linearly dependent solutions. Maybe it's not useful. Well, here is a fact, or rather a theorem. So let's say A and B, let A and B be n by n matrices, or rather, let's say m by n, because I'm using n as an index. With AB is equal to BA. So they're commuting matrices. Then e to the a plus b is equal to e to the a times e to the b, which by a consequence, since a plus b is equal to b plus a because addition is commutative, then this is also equal to e to the b times e to the a. So if matrices commute, then so does their exponential. And in particular, the common value of these two things is the exponential of the sum. So here's a proof. And it's going to use the binomial theorem. So let's just look, I'm going to do a preliminary remark. And that's that what happens if I take something like a plus b squared and I do it in the strict definition. A plus b squared, strictly speaking, means a plus b times a plus b. And what that's equal to is a squared plus a b plus b a plus b squared, right? Now, in general, these two things won't be equal, right? In general, for matrices, it's not true that a times b is equal to b times a. However, our hypothesis was that they commute. So since they commute, and the way that we write that they commute is if we write a b in put braces around it, then that means the commutator. That means ab minus ba. Since ab minus ba is equal to 0, this is equal to a squared plus 2ab plus b squared. And so as a consequence, we're going to be able to do this with all higher powers as well. And so what happens when we rearrange them to have all of the a's before all of the b's is that we're going to get the binomial theorem. Thus, a plus b to the power of n is going to equal to the sum from, let's say, k, or sure, the sum from k is equal to 0 to n of n choose k, a to the k, b to the n minus k. And this is just the binomial theorem. And this only holds when a and b commutes. So this is defined as the commutator, which is ab minus b, a is 0. Okay, so with that preliminary remark out of the way, let's consider e to the a plus b. By definition, this is the sum from n is equal to 0 to infinity of a plus b. So really, here I had a t when I defined this. I mean, I just substitute whatever this is to the power of n. So the formula defines this. Now we're going to use the binomial theorem. However, the binomial coefficient can be expressed in terms of factorials as well. So if we think about it, what is n choose k equal to by definition?
N factorial over k factorial over n minus k factorial.
Good. So that n factorial at the top is going to cancel this n factorial at the bottom, right? So what we're going to get, we can write it as a to the k divided by k factorial and b to the n minus k divided by n minus k factorial. Now we're going to do a very clever rearrangement of this sum. basically what happens is that here you have all possible pairs n and k, where k is less than or equal to n. But what happens is that that gets distributed across these two numbers. Well, what I'm going to claim is that this is actually equal to the sum from n is equal to 0 to infinity, and the sum from k is equal to 0 to infinity. Notice that this n changed to an infinity of a to the k over, let's say, a to the n times b to the k over k factorial. And the reason is, let's imagine all possible, or you know what, maybe I'll introduce different letters. Maybe I'll introduce I and J. Just to clear up the confusion as to how these two things are related. I is not the imaginary unit, it's an index in this case. So how does this work? Well, if you consider any such pair, then you have their sum, I plus j, and k is going to equal I. So how this works is that we're going to make the substitution. N is equal to I plus j, and k is equal to I. And with respect to the substitution, all possible pairs I and j become all possible sums, and then k ranges up anywhere up to the value of the sum, depending on whether j is 0 or not. So these two sums have the same terms. It's just a rearrangement. Do you have any questions about that? So this might take a while to see. So what happens next is that this only depends on I and this only depends on j. So we can basically factor this thing out of the sum, and this is the same as the sum from I is equal to 0 to infinity of a to the I over I factorial times the sum from j is equal to 0 to infinity of a to the j over j factorial, which is equal to, sorry, this is b. Which is equal to e to the a times e to the b. So using the binomial theorem, which only holds because they're commutative, and then doing a very clever rearrangement in reindexing, we're able to write it as a product of two exponentials. So this proof is non-examinable. I'm not going to actually test your ability to reproduce this proof. But anyway, that's how it works. So, and this is part of the course material as it usually stands. The list says matrix exponentials. So what's a corollary of this? Well, e to the t plus s, if t and s are two different numbers, a, that's equal to e to the ta times e to the sa, right? Because if you just scale t by a number, it commutes with, if you scale a by a number, it commutes with a scaled by a different number. Because TA commutes with SA. Right? But what's a consequence of this? Thus, e to the TA times e to the minus TA is equal to e to the 0. Let's write 0 times the identity matrix just to show that it's an exponential of a matrix. It's the exponential, or let's say, of the 0 matrix. And rather, we were saying it's an m by m matrix, right? Well, what's that equal to? That's by definition equal to the sum from n is equal to 0 to infinity of 0 to the power of n divided by n factorial. But that's the only non-zero term is going to be 0 to the 0 over 0 factorial. And all of these things are defined. 0 to the 0 is actually the identity matrix divided by 1. So this is actually the identity matrix. That's how it works. The question was, what is the base case of this? Well, the base case really in this definition is that it was the identity matrix. So e to the at is always the identity matrix plus stuff. But this means that e to the at is invertible. E to the ta is invertible. Implies the solutions are linearly independent. So the columns are linearly independent solutions. So I have given you a formula, which is an infinite power series, so it's not necessarily a very useful formula, for being able to solve a homogeneous linear system with constant coefficients by way of calculating this matrix exponential. And it was very important that there was a constant coefficient thing. Why was it very important that it's a constant coefficient thing? Because when we took the derivative of this expression, we didn't have to apply product rule. If we had to apply product rule, then we'd have a primes here, and that would not give us a solution. But what's a very interesting thing about this? So e to the at is defined by a clear formula. That means that the solutions that you get from this, they're sort of canonical. It's a canonical basis of solutions. And they have a specific order. So in general, you could take the solutions and you can take linear combinations of them and you can get another basis of solutions. Well, this actually gives you a preferred basis of solutions that's ordered in a preferred way. And I find that very interesting. So it turns out that the problem actually has a preferred set of solutions that's given by calculating this matrix exponential. Okay, so let's do an example of where we're actually able to calculate the matrix exponential. Suppose that A is equal to the matrix, let's say lambda 1, 0, lambda 1, 0, 0, lambda 0. And so I'm going to say that A is equal to lambda times the identity plus a matrix, which I'm going to call n. And I'll explain why I call it n in a second. And this is where n is the matrix that looks like what?
With like a small upper diagonal.
Yeah, so one's on what's called the super diagonal. Okay, cool. Now, what's the property of n? The cool thing about n is that n squared is equal to, we calculated this last time. So the only non-zero entry that you'd get is this times this, which gives you a 1 in the top right entry. And n cubed, on the other hand, well, what's that?
All 0.
Yeah. So this matrix satisfies the property that some power of it is 0. So N is known as a nilpotent matrix. That's why I use the letter N for it. And the key is that for nilpotent matrices, we can calculate what the exponential is. Why? Because in this infinite sum, most of the terms are zero after a certain point. So that's why we care about nilpotent matrices. So N is nilpotent, meaning N to the K is equal to 0 for some K. Here, K is equal to 3. Okay, now if we want to calculate e to the AT, what that's equal to is e to the lambda ti plus tn, right? Now, does a multiple of the identity matrix commute with n?
I would say yes.
Yes, because the identity matrix commutes with everything. The identity matrix, when you do matrix multiplication with respect to it, it doesn't change the matrix. That's the property of the identity matrix. So because these commutes, so because the identity commutes with everything, we can write this as a product of exponentials, e to the lambda ti, e to the tn. And then I'll write equals to star. Now let's think about e to the lambda ti. This is equal to the sum from n is equal to 0 to infinity of lambda t to the n, and then the identity matrix to the n. But the identity matrix, any power of it is just the identity matrix, including the 0th power, right? So what that's equal to is just the sum from n is equal to 0 to infinity of lambda t to the n over n factorial times the identity matrix. And this is a number. What number is this equal to?
E to the lambda t.
Yes, because this is the power series expansion of e to the lambda t. Good. And on the other hand, e to the tn, well, that's equal to this infinite sum as well. N to the t times, sorry, n to the n, little n, t to the n over n factorial. But that's equal to just the terms up to n squared, because n cubed onwards is 0. So that's equal to the identity plus n t plus n squared t squared over 2, right? And so what that's going to look like is, well, the identity is just the diagonal, n is just the super diagonal, and n squared is the second super diagonal. So that's going to be 1 t squared over 2, 1 t, 1, 0, 0, 0, right? So what does star equal? Well, what we have is that this is just a multiple of the identity matrix. So it's just going to, that the identity doesn't matter. So it's going to be e to the lambda t times this matrix. I won't rewrite it. I'll just copy it. Cool. So in general, so we've solved that example. So in this case, we were able to calculate the matrix exponential because we had a nilpotent matrix, which made things easy. Well, it was rather this. Okay, let's consider the general case, this general case. In general, if we have a M by M matrix of the form, so lambda's on the diagonal, and one's on the super diagonal, and then zeros everywhere else. Does this make sense as a matrix? So zeros everywhere, except for lambda's a diagonal and one's on the super diagonal, and it's an M by M matrix. So it's just a generalization of the previous case from being a 3 by 3 example to an M by M example. Then that's equal to lambda I plus n, where n has ones on the super diagonal. Then n to the m is equal to 0. And n to the k for k is less than m has ones on the, I'll say, the kth superdiagonal. Where sort of the 0 superdiagonal is the diagonal. So the 0 superdiagonal is the diagonal. The first superdiagonal is the superdiagonal. The second superdiagonal is ones just above this, and zeros everywhere else. This does not hold for negative powers, by the way, because n is not invertible in the first place, so there are no negative powers. Okay, so what is the consequence of this? So if this is A, then e to the AT is equal to e to the lambda I t, or let's say lambda ti, by e to the tn. And the reason is that the identity commutes with everything. So because of commutativity, and only because of commutativity, we get this. And what that's equal to is, as before with the identity matrix, we're just going to get e to the lambda t times the identity matrix. And then what we're going to get for e to the tn is it's going to be I plus n plus n squared, plus nt plus n squared t squared over 2 plus dot 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 plus n to the power of the highest it's going to go is k minus 1 times t to the k minus 1 over k minus 1 factorial.
You mean m?
Yes, m. Also, I should write this, it's too squished. A bit squished, but whatever. Okay, so that is e to the AT. It can also be written as in this pattern. So once here, then this is n, so it's just on the super diagonal, we have t. On the second super diagonal, we have t squared over 2, all the way up to t to the m minus 1 over m minus 1 factorial. Then 1, then t, then it goes on, and then we have 1, and then we have t here, etc. And then zeros here. So notice, by the way, this is going to be amazing. So we have a solution to these systems in general, right? Well, let's see how much time we spent last class solving this example for a 3x3 system or a 4x4 system, because we did it and it took us a long time. So if I go to the previous lecture, in the previous lecture, sorry, it was not L6, it was L7. In lecture 7, we considered the first example was a 4x4 system. And the 4x4 system was exactly 2s and then 1s on the super diagonal, right? And let's see what we did. So we did a calculation to determine that the eigenvalues were 2. Well, okay, of course they are. Why are the eigenvalues 2? Actually, no, that reason doesn't work. And then what we did is we actually found sort of iterated basis for this, where each thing mapped to the successive thing. And then we found these vectors, and they were the unit vectors. And then what happened is we used our onsoughts. And remember that the onsoughts was a very clever idea. We actually had to come up with this super clever idea that the onsoughts would be t squared t cubed over 6, right? Well, we get that for free. That entire onsoughts, it comes for free from this idea of matrix exponentials. And then after putting all of these together and doing a lot of arduous work, we got into this system. Well, sort of, if you look at what the fundamental solution is, then C0, 0, 0, T1, 0, 0, T squared over 2, T 0, 0, T cubed over 6, T squared over 2, T1. That's the matrix reading the columns down, which is exactly what we got here. Sorry. Okay. So bam, we've solved that. And we didn't have to do it like we did last time. It's just this a few observations gives us another solution for that, right? Now you may be thinking, oh, okay, so is everything much easier now? Well, unfortunately, it's not much easier now. If we actually want to see how this is related to the previous example, the problem is that if you have something like this, what the name for this is a Jordan block. This is what is called a Jordan block. And now I'm going to talk about the Jordan decomposition theorem. And the claim is actually going to be that in general, to calculate matrix exponentials, it suffices to know how to exponentiate Jordan blocks.
Maybe once you like exponentiate the Jordan block, like since it shifts up and then you add a bunch of those to, oh, never mind.
So the claim is that sort of by changing basis, oh, okay, let me also just indicate sort of another obvious thing. So observation. If A is of the form, let's say A1, this is some matrix, and then sort of the matrix is split into blocks, and everywhere else you have zeros. So this is known as a block decomposition. And in general, we can consider any number of blocks. The point is that you'd sort of have blocks along the diagonal. So it's like a diagonal matrix, except for the fact that instead of having just a diagonal is a block matrix in which all of the blocks are 1 by 1 size. So this is a block decomposition. And in this block decomposition, these are square matrices. So they have to be square in a block decomposition. Well, what happens basically is that if you take a to the power of k, that's the same as a1 to the power of k, and a2 to the power of k. So as far as products of the matrix with itself are concerned, blocks do not interact. So blocks are non-interacting. So if your matrix consists of Jordan blocks, then you can calculate the exponential in each block individually. Okay, well, not every single matrix is Jordan blocks, except for the fact that it is if you change basis. So let's go to the example that we did last time. Last time, we considered the second example, which was this one, right? So we considered this example. And what did we do with this example? Well, we wanted to find sort of the structure of this example. And what do I mean by the structure of this example? Well, what we found, and we were able to summarize the information, was that we had this set of generalized eigenspaces given by certain things mapping to certain things. And this is what I will refer to as the structure of a matrix for a reason that I will make clear. We had and so this actually gives you the structure of the matrix. So let's say that this is going to equal V1. This is going to equal V2. This is going to equal V3. And this is going to equal V4. Then what we have is that A of V1 is equal to 0, right? A of V2 is equal to negative V2 because it's an eigenvector, right? A of V3 is equal to, well, it's going to equal V2 minus V3. And A of V4 is going to equal to, well, V3 minus V4. So there is a notion of writing a matrix with respect to a basis. So how you think of writing a matrix with respect to a basis is that you write what the basis is on the sides of the matrix. And what you're going to do is you're going to write how A of V1 can be expressed in terms of the other vectors. So what is A of V1? Well, A of V1 is 0, right? So in terms of the other vectors, it's just 0. So A of V1 is 0, right? It's 0 times all of the other vectors. Well, what is A of V2? A of V2 is minus V2. So it is 0 V1 minus 1 V2, 0 V3, and 0 V4. That's exactly this equation. What is A of V3? A of V3 is V2 minus V3, and then 0, and then 0 here. And A of V4 is V3 minus V4. So what do we see? We see that we actually have the matrix in a block decomposition where the top block is a diagonal matrix with 0 along the diagonal because that's the eigenvalue. It's the eigenvalue 0. And here we have a Jordan block corresponding to the eigenvalue -1. And it's a 3x3 Jordan block. So this is a Jordan decomposition. By the way, so what is this equal to? So let's call this matrix J. Then what happens is, let's consider the matrix Q, where that matrix is equal to a matrix whose columns are V1 through to V4. So this is going to be the matrix, well, let's see, 1, 2, 1, 1. Then we're going to have 0, 1, 0, 0, 0. Then we're going to have 0, 2, 1, 0. And then we're going to have 0, 1, 0, 0. So what property does V satisfy? Q satisfy? Q times the unit elementary I vector is equal to Vi, right? So if you start off with the usual basis, which is just a 1 in the I position, then it sends that to Vi, right? So the result is that A is equal to Q inverse. This is going to be a basis, so it's going to be invertible. Q inverse JQ. So how you think about this is that if you're starting from this side, you start off of the unit basis, then it's converted to the VI basis. And in the VI basis, the matrix is J, and then you convert back from the VI basis into the EI basis. So by the way, this isn't that important to understand because this isn't actually going to come into calculating any examples. I'm just going to show you what the general, how this connects to how we solved examples before. Well, what's the key property? If you take something that's this is known as conjugating by Q. Well, what happens if we take Q inverse JQ? And what happens if we square it? Well, by definition, that's equal to Q inverse JQ times Q inverse JQ, right? But the Q's cancel out. So we get Q inverse J squared Q, right? And in general, this happens for any nth power. So if you have a conjugate of some matrix and you raise it to the nth power, then that's the same as just Q inverse J to the NQ. Do you see that? Okay, so what's the lesson? Well, that means that if we want to calculate, thus e to the a t is equal to e to the q inverse j q t, which is equal to q inverse e to the jt q. Because you do it for every term of the power series expansion. Thus, if you're able to calculate what Q is thus, if we do all of the work that we did before and we find this thing, then that actually gives us the structure of the matrix. This is the structure of the matrix. So the result is that every single square matrix, also known as an operator, every operator has a structure, and the structure is given by this type of pattern of what the generalized eigenspaces are. And then if you take the vectors that you have in the structure and you change basis with respect to those vectors, then you get a Jordan block decomposition. And then you can exponentiate each block individually. And then you have to conjugate by Q again. But that means that you have to find Q inverse. And so this solution isn't any easier than the solution that we had before, because how did the solution that we had before work? Most of the work was put into finding this structure, right? That was most of the work. And so here, after finding all of that structure, well, the exponentiating J is easy, but then you have to invert Q, and that's a bit annoying. So this is actually more work. So in the end, calculating the exponential is more work than what we did before. Is, let's say, a tiny bit more work because you just have to calculate Q inverse, whereas you didn't have to do it last time. However, it requires less cleverness because there was cleverness last time, and that was this onsatz. And this onsatz might have come out of thin air. I could have motivated how it worked, but you had to have that idea. In this approach, you don't have to have that idea. You just compute the structure, and without the onsatz, you get it. So we won't be solving problems this way.
If we didn't have like that e to the at was, if we had it was only defined for like what we had before, then it wouldn't make sense to take a derivative, would it?
So the power series converges because of the n factorials. And the power series, this is the pure math thing. It doesn't just converge, it converges absolutely. And if you have an absolutely converging power series, then you are allowed to take term by term derivatives. If it did not absolutely converge, then you would not be allowed to take term by term derivatives, but it is an absolutely converging series. So that's the catch. So we won't be solving problems this way. However, this is actually super useful. For what? What does this give? That's super useful.
Computers?
Exactly, 100%. This is a useful numerical algorithm. So computers can use this. Computers would not calculate the power series to infinity. they calculate it to some point to get a numerical approximation to the solution. So by calculating the series to some large n, or by doing the Jordan decomposition, or exactly by doing the Jordan decomposition. But that's no easier than implementing the other algorithm. So this algorithm, this is sort of hard. If you want to do it exactly, this is hard to implement. However, calculating the series to a large n, that's easy to implement.
Where would like differential equations like this come up?
Well, okay, you got me there because this course is technically called Calculus 4 with applications, and I actually haven't been doing any applications at all semester. However, we have like half the course to figure that out, so I'm probably going to actually tell you later. This is exact, but ignoring the exact thing, so this gives an approximation. That's easy to calculate. So it actually gives the nth Taylor series approximation of what the actual solution is. But I have to say, you have very good intuition for realizing that it was a computer thing, because that's 100% right. So this is a numerical algorithm, and that's sort of the most important thing about this observation, because in the end, it was like, oh, cool, so you can solve it this way. But how easy it is to actually calculate matrix exponentials because they're an infinite series. Well, for Jordan blocks, it's easy. But finding the Jordan decomposition is basically involves all of the work that we had to do before. So it's not actually that much of a boon. Okay, so now let me show you something. This is going to be interesting. I'm going to quickly change what I'm screen sharing to my browser. So I guess this is the department homepage. If we go to undergraduate courses and we go to 303, then what is the topic list? First order ODEs, existence and uniqueness of solutions, where we haven't actually talked about existence and uniqueness theorems, but I've sort of mentioned what they are. Separable, goods. Population growth logistic equations. I guess this is an application. General or nth order linear equations and initial value problems. We did general, this is with constant coefficients, I guess. We talked about how you'd find the eigenvalues, well, solve the polynomial. And then I sort of sketched how it works in n dimensions. Wronskians, sure. Linear equations with constant coefficients using characteristic equations. Well, that's what I was, I guess, talking about before. And general nth order linear equations, the idea is that it's linear. So for the homogeneous equation, you're going to get a n-dimensional space of solutions. And then for the inhomogeneous equation, there's going to be a particular solution. So that's what you can say about these in general. But then for the linear ones, that's using the characteristic equation. Great. Variation of parameters, linear systems, first order linear system, and matrix exponentials. Okay, so apart from like this is applications, and apart from maybe more rigorously discussing the theorems, we are 8 out of 15 lectures in, and we have actually finished all of the material in this course. So yay. Okay, now I said that today was going to be a short lecture, but it's already 8:19. And I prepared a tiny bit more to talk about operators, because that's what we ended up with talking last time. But I sort of can't get to any punchlines. So I can either spend 40 minutes talking about that now, but I'm not going to get to any main points, or I can just end the lecture here and go for next time. And so I do actually have like 40 more minutes of material. But it's not going to be satisfying to see it now. And we just reached a good stopping point. So I think I'll call it there. Any questions? but yeah, so like this, I can, I guess, make some general remarks about the material in this course now that we've finished the material in this course. So I did not, I guess I told you what the backstory was. In undergrad, I did not take any ODEs courses because I didn't have to. And I made it a point of pride that I wouldn't. And then I took a course on elliptic partial differential equations, which was a pure math course in which we did not solve any differential equations at all. It was about proving things about solutions, and it was like the stuff of nightmares. But in high school, in grade 12, I sat in on a bunch of classes at U of T. So in the first semester, I did complex analysis. And in the second semester, I sat in on 3 things, but then really at the end, I only sat in on this differential equations class, and it was taught by Victor Ivry. And I emailed him later and I actually asked for his notes, and then I've been using those, and I showed you some pictures from them. But like I basically learned this material in high school, and most of what we covered is basically exactly from his notes as well, except for the fact that he sort of assumed the linear algebra. So for the linear algebra, I went to the last offering of this course by Kevin Sokol, and I used his notes a bit. So Ivry's notes are secret because he shared those with me in confidence, and they're from a different university. But Kevin Sokol's notes, which I can show you where to find them, are good. So this is a resource that I'll tell you about. So if you just go to the course webpage, Math 303, and you click on the Spring 22 offering, this is by Kevin Sokol, and there is just like lecture notes for every single lecture. And so this is useful. And then he covers like, here's multiple eigenvalue solutions. So he ends with linear systems, and you have like, okay, sure. So what happens if there's a multiple solution? So yeah, in the first case, if it's just a diagonal matrix like this, there it's a 2-dimensional eigenspace, great. But in this example, so I was basically copying the examples from him when I was doing this section, and everything else is from Victor Ivry's notes. He says, okay, well, here we can solve it, uses like a first order linear equation. And that gives us solutions, but then we only get one eigenvector. So how do we proceed? And then he does what I did. So, okay. So let's just look at the next 2 notes. And the examples are exactly the same. I just pulled this material from his notes for this. And then he solves that, great. And then he talks about these chains. And then he talks about the onsets that you get in general. And then he does 2 examples. The first example is one's on the superdiagonal. I put 2s here because it was sort of boring. I thought it was nicer to actually have something on the diagonal, and I did that. Okay, so he does the same thing. We've already seen this. Then he does this example, which was the second example. But he doesn't actually do any inhomogeneous systems. Victor Ivry has that in his notes, but he doesn't actually do any examples. So I had to look up examples online for some actual nice numbers. And then if you look at his other notes, it's basically the same thing that we were doing, except this is 41 lectures. This is lecture 8, right? So 8 times 3 is 24. So in 24 lectures, we have covered what was covered here in 41 lectures, except for the fact that there was several lectures on numerical methods, which is what I guess what I'm going to do this first part of the end of the course. And then there was also a bunch of applications, which I should also do. So we're going to get the applications. But I think I liked doing, putting all of the actual theory, well, theory in the sense of how do you solve differential equations, not theory in the sense of existence and uniqueness theorems. So like, if we look at these topics, what is there? Well, okay, so, okay, then there's some discussion of why are differential equations useful, which I haven't talked about at all. Sure. Then slope fields, and so this is important, of course. What's the intro? Oh, I didn't even look at the first few. He actually had slides for the first few. This is the first time that I'm seeing slides. Well, yeah, so he gives this interpretation of things of the form dy dx equals fxy as being fields of slopes. I call them direction fields. And then how to find integral curves of direction fields. Okay, great. And then what happens? Okay, linear first order equations, great. We talked about 2 ways to solve them. There was the method of integrating factors, and then there was the method of variation of parameters. And both of those got generalized. So integrating factors got generalized to integrating factors for exact differential equations. And you can actually show that the integrating factors for first order equations are a special case of integrating factors for exact differential equations. So if you treat your first order equation as an exact differential equation, then actually one of the dividing by m or dividing by n, one of them always works to give the integrating factor that you usually get in this method. And then the other method, which was variation of parameters, got generalized a lot to basically being able to solve any linear system in homogeneous linear system. So both of those got generalized. Substitution methods and exact equations. What is substitution methods exactly? So I'm about to find out for the first time because substitution in the sense of making a substitution to make the problem simpler. So like, for example, for homogeneous equations, we used a substitution, or I called it an ansatz instead of a substitution. And then similarly for they were called Bernoulli equations, right? Bernoulli equations was another type of substitution. Okay, and then he's talking about integrating factors, great. Okay, equilibrium solutions and stability. This is actually more on the application side. So here are population models. This is application side, acceleration, velocity, and then numerical methods. So if we look at this, this is like 1, 2, 3, 4, 5 lectures of applications. And at the pace that I'm doing, 5 lectures is about one of my lectures. It's a bit less than that. I'm going at a bigger pace. Okay, second order differential equations. Great. General solutions. So this is going to be variation of parameters, probably. Again, I was using Ivry's notes, so I'm looking at this. Okay, so this is basically if you have constant coefficients, then you depend based on the values, there's sort of a split. These are complex, these are double roots, these are distinct real roots. And then there's also, yes, so you get stuff. Okay, yeah, superposition, existence, and uniqueness. The other thing that I didn't do in this course is that people care about initial value problems. So they don't care about finding the general solution, they care about finding a solution with specific initial conditions. And what that amounts to is plugging in numbers and solving for your constants. And I did not want to plug in numbers at the end of every single problem that I did. So I just didn't do it because I could not do it. And so, yes, I guess when we're doing applications, if you have, for example, an nth order system, then the initial conditions look like not just giving the initial value, but also the first and the second derivatives if it's a third order equation. So we can talk about that more next time. Or maybe not next time, but when we get to the applications. Okay, yeah, homogeneous equations of constant coefficients, nth order ones. I guess I can say a bit more about nth order because I mostly just did second order, but it's sort of the same thing. And if you have repeated roots, then you're just going to multiply by t repeatedly. Cool. Okay, mechanical vibrations. So this is like 1.5 lectures of applications. So we're 6, 7.5, maybe 2 before 8, 9 lectures of applications. Undetermined coefficients. So undetermined coefficients is not variation of parameters. That was sort of when you had exponentials, how you handled that. Okay, method of elimination is reducing a system to equation, which doesn't always work. And then there was all of the linear algebra stuff. So like, yeah, that's the course. And I guess we're going to do applications and then just fun other things to solve it. I'm not going to do like specifically advanced stuff, but we have half the course left. Cool. So that was basically an overview of the material. And so I didn't remember any of this material because I learned it in high school, but that was like 11 years ago or 10 or 11 years ago, one of the two. And I mean, at the rate that things are going, I really can't work on these lectures until the day of the lecture, but it's at 6. So it's like 5 hours of work before that. And then I relearned all of this material by just reading things. It's 5 hours for a 3-hour lecture because I actually have to understand all of the material and then think about it and then write notes. So it's like 2 hours of reading and then 3 hours of writing notes. Yeah. And as for actually like grading your homework, okay, well, that's sort of last priority. What I need to do is I need to write the assignments. And I really should have that out by tomorrow or else we're falling back because I said it would be due a week after. Oh, and shoot, the most important thing. Okay, we need to do a midterm. And I should have announced when this midterm was happening way ahead of time, but I'm feeling not this weekend, the weekend after that. I'll make it a whole weekend's take-home midterm. So if you have weekend plans, then you're unfortunately going to cancel them because if I tried to schedule a midterm on any other day, people would have conflicts and it would be annoying. But if it's weekends, then I can say, well, okay, I'm going to give you more than a day, so it's fine. You can do it in a day, but have at least a free day on the weekends. And I'm going to send an email about this, of course, because there are more than 7 people registered for this class. And I don't know what the other people who don't attend lectures are doing. Maybe after the midterm, maybe it's already too late to drop out. But yes, hopefully people are who, like the half of the class that's not attending lectures is watching them, because otherwise that's pretty awkward. But okay, midterm the weekend after this one. Assignment hopefully out tomorrow. I need to send notes for both classes as well. And then grading is last priority. So writing the assignments and the midterm trump grading. So eventually, maybe, I think grading will happen, but don't expect it in this weekend because I also have to do research. I have an important research meeting on Monday and I need to prepare for that. I need to read a big paper. And then this morning before the lecture, I started working on at like 1. Before that, I have a meeting with my advisor on Friday. Yeah, so tomorrow, and I need to send her some code. So that was a thing. And then I'm also teaching another lecture for this homotopy type theory summer school on Saturday, and then I'm also attending with a lecture and helping with the Q&A tomorrow. So that's what I'm up to. Anyway, that seemed like a fun sort of social thing. So yeah, material of the course except for applications basically done. And that was some interesting material in my opinion. So good. Okay, see you on Monday, and hopefully I will keep my promises and send things out soon, hopefully by the end of tomorrow. Bye.